Welcome to video 13.2 for a discussion of the colored complexes that form with transition metal ions. Gotta love chemical humor. Accessing your prior knowledge should include remembering electron configurations of atoms and ions for d-block elements, and complex ion formation for transition metals, and the idea of a ligand from 13.1. The big idea for 13.2 is that d orbitals have the same energy in an isolated atom, but split into two sublevels in a complex ion. We'll give that some detail, don't worry. The electric field of ligands may cause the d orbitals in complex ions to split, so that the energy of an electron transition between them corresponds to a photon of visible light. Huh? Yeah. We'll come back to this big idea throughout the video. Maybe not directly to this slide, but we will go through the ideas in this big idea so that they make a bit of sense beyond just an isolated two-sentence statement. There are a number of syllabus statements that we will cover. So let's look at the electron configuration of a number of different ions of the transition metals and their colors. I want you to notice two in particular: zinc 2+ and scandium 2+. What do you notice about the D shell in those two scenarios? The D shell is full here, and the D shell is empty for scandium 3+. But all of the others have an incomplete D shell. That's important. So these transition metals form complex ions that have a variety of different colors, as you saw on the previous slide. So what makes the color, and how does the color kind of work? Well, I've got a diagram here for you that shows a yellowish orangish solution, and white light consists of all of the colors, and that white light is shining onto the sample, and the blue light is absorbed. And when blue light is absorbed, the complementary color is kind of an orangish yellow. So that's the idea of a color wheel and complementary colors. So the color absorbed, so let's say green is absorbed, that means the substance would appear kind of reddish violet. If orange is absorbed, it's going to appear kind of greenish blue. If yellow is absorbed, it should appear kind of violet. If violet is absorbed, it should appear kind of yellow. These complementary colors are helpful to remember, and the mechanism of colored solutions. The IB gives us a color wheel. We don't need to memorize it. These transitions are not necessarily equidistant in terms of the change in wavelength. I think this is a general guideline. It's not perfect in every scenario, but certainly it plays a role in our discussion of color. In the essential idea syllabus statement, the idea of the orbitals, or the energy of the d orbitals being degenerate in an isolated atom was mentioned. But when there is a ligand, the orbitals actually split into two levels of energy. And that splitting in the presence of a ligand is important. So as an example, if there's an electron in the lower energy level of the 2D, sort of call them sublevels, this electron will absorb green light and be promoted up into the higher energy level. And by absorbing green light, if I look at the color wheel, if it absorbs green, it will appear red. So this splitting of the d orbitals means that these electrons can be promoted by the absorbing of light, and the amount of energy it takes to promote that electron happens to be somewhere in the visible range. Based on the color that is absorbed, we can see the complementary color. We can observe the complementary color. So we've got some more syllabus statements to discuss, all related to the color of these ions. Factors that affect the color: identity of the metal and the charge on that metal, the charge density of the ligand, the geometry of the ion, and the number of d electrons present, and hence the oxidation number of the central ion. So let's look at these factors. First of all, the identity of the metal and the charge. Ligands interact more effectively with the d orbitals of ions with a higher nuclear charge. A higher nuclear charge attracts the electrons of the ligand. So if I look at manganese 2+ and iron 3+, they both have the same number of d electrons. But since iron has a higher charge, it has a higher energy of light absorbed. So let's take a look. If this iron appears kind of yellow, it is absorbing violet. And this appears kind of a reddish pink. If it's red, it's absorbing green. And so violet is a higher energy light, shorter wavelength, higher energy. So we can see that the iron is absorbing at a higher wavelength. So that means if I look at the d orbitals in the iron complex have a greater energy difference than the d orbital split in the manganese complex. Notice that this distance, this energy difference, is greater for the iron than it is for the manganese. Greater distance, greater difference in energy means a higher wavelength of light is absorbed, and violet was absorbed here, so it appears kind of yellow, whereas here green is absorbed, so it appears kind of red. The other thing that can affect it is the charge density of the ligand. We have a number of different ligands, from iodide to carbon monoxide. The shortest wavelength, highest energy, the strongest ligand. Iodine or iodide ion is going to be the weakest ligand. So we can use this to make a comparison of a relative comparison. So stronger ligands with the same metal will produce a greater difference in energy. This energy difference will be greater for the stronger ligands if I'm comparing two ligands on the same metal complex. The spectrochemical series is given in our data booklet. And this is really meant to be a relative comparison. It's not going to give us an exact, like, okay, if you've got thiocyanide, it's going to give you yellow. It's going to absorb yellow. We don't know the exact colors it will absorb. This is a relative comparison. So let's take a look. I have ammonia and I have hydroxide. Ammonia is a stronger ligand than hydroxide. And ammonia is violet, so it absorbs yellow. And hydroxide is green, so that means it absorbs red. Yellow is a greater energy. Speaking here about energy, yellow is a greater energy light, a higher energy light. So a stronger ligand, ammonia, creates a greater difference in energy between the d orbitals that split, so it absorbs a higher energy light, yellow compared to red. The geometry of the complex is also something that affects the color. However, if you look at the applications and skills from the IB, geometry is not listed, and that means we don't really study geometry. Truthfully, it's a very complex interaction. You could spend a week studying transition metal complex ions, like an hour a day, every day for 5 days, and not get all of it. There's so much there. So we're going to skip geometry because it's not required by the IB. The number of electrons present and hence the oxidation state of the central ion is important. So if I look at iron as a 2+ and as a 3+ ion, iron is yellow, yellow-orange if you will. And so that means it's absorbing kind of in the violet-blue area. So this is absorbing violet or blue. Oops, I didn't spell blue correctly. Sorry about that. Come on now, spell correctly. So violet or blue, and if I look at this kind of a green color, the green is absorbing red, so this is absorbing red. So the violet blue is a bigger energy difference than the green. This is the change in energy for the green. This is the change in energy for the yellow. Violet blue is higher in energy, so it represents a bigger difference in energy for these electrons that are split in the d orbitals. Such a thing exists as a polydentate ligand. Poly means many. So a polydentate ligand is one single ion or one single compound that has multiple sites to form a coordinate bond. Remember, these ligands form a coordinate bond. And so here I have 1, 2, 3, 4, 5, 6 lone pair sites on this atom that can form a ligand, a single ligand with 6 coordinate bonds around this metal ion. EDTA is a pretty common polydentate ligand, and it is used as what is called a chelating agent to remove transition metals from a solution. Maybe there's an IRP in there somewhere. Our data booklet has a couple different, well, 3 to be specific, 3 different polydentate ligands. These are bidentate. They have 2 locations where the ligand can make a coordinate bond, and this is a polydentate in terms of having multiple sites, as you saw from the previous slide. And there we go. That is our introduction to colored complexes. Certainly it's related to electron configuration. It's related to our study of the electromagnetic spectrum from topic 2 as well. In terms of a summary, transition metal complex ions are colored due to the splitting of the d orbitals into 2 sublevels, as we talked about. So the d orbital splits into 2 different energy levels, and that difference allows an electron to be excited by the absorbing of a particular color of light, and it is the complementary color that is visible for the complex. Anything else you'd like to add to the summary? Now's your opportunity. Checkpoint question, multiple choice question 1. Which of the following salts form colored solutions when dissolved in water? Pause the video, give it some consideration, come back when you're ready. And the answer, if you're ready, is B, 2 and 3 only. Scandium is not a transition metal. Well, scandium is a transition metal because it has 1 d electron by itself, but the scandium 3+ ion has no d electrons, and the zinc 2+ ion has D10, 3D10, so it's a full D shell. So they do not form colored complexes. So this is a bit of, I don't know if you'd call it memorization, but a bit of remembering that scandium 3+ and zinc 2+ do not form colored solutions. The rest of the transition metals typically will. Thank you for listening. Much appreciate your attention. Have a great day. I'll see you in class.